Hello. Good morning.
Good morning, sir.
Are you able to hear the voice properly?
Yes, sir.
Let us wait. Others can also join. 2 minutes. I'm sorry. Due to some occupations, I could not able to engage the classes earlier, even though it was scheduled. Again, today, due to some pre-commitment, we exchange between the Nagai sir and myself.
Yes, sir.
The voice is clear. Amadan, Deepika DN. I have no difficulty in login to this page. Okay, I'll start. Let us see that. I'll share the screen. Others can also join in due course of time. Okay, no issue. Let it be there. We will discuss, then let them join. Others also can join. See, welcome to you all for the teacher program. Almost 10 year for the first batch who has started from 22nd of the October to be in area 2, and for the others also. The first paper, you are well aware that actually it's going on well by the seminars and other part of the discussions. The second paper, the faculty members are teaching different faculty members. So the first unit is shared between me and Professor Vijay Kumar Hestodamini, who is an very expertise in the astrophysics and astronomy, including the cosmology. My part is related to the relatively with the atmospheric physics to a great concern. The first title goes in such a way that the research techniques in atmospheric physics. The very much the people from this university and also from the others are well aware of this campus. I hope you are well adjusted with this. This is the case. As the thing goes, the topics, whatever it was assigned for the second chapter, or you can call it as a subunit of the first unit, lies with the thing research techniques in astrophysics and atmospheric physics. Of course, astrophysics will be dealt by Professor Dodmari sir. I will take up the second part, or later half of the part actually. Broadly, one can classify this unit into 5 major topics, which are shown in red in color. And the subtopics which belongs to that, of course, it is a continuation of the topics only, are shown in the green in color. The first one goes with the electromagnetic energy, or electromagnetic spectrum also they can call sometimes actually. Then the last regarding the amount of the energy which are radiated from an object, where you can deal with the different 3 laws, basic laws actually. Then the concept of the black body with the emissivity and also the dependence of the temperature and wavelength bands. Earth and its atmospheric layers, it's a broad view. Then atmospheric effects, for example, like scattering, absorption, reflectance, and then the gain size, particularly the aerosol size they can call, or the atmospheric particle size, how that influences the scattering processes they can call, for several processes. Let us restrict our discussion. I'm saying that it is discussion. It is not one way of only I am telling and you are listening to me. Of course, you can interact either in the middle or even at the end also, doesn't matter. Or even after the class also, you are having more freedom to interact with us actually, not be alone for all of them. If being research actually, see, the thing is that till master degree, you learn the topics from only the faculty side. But in research, it should not happen. There should be and vice versa. The learning has to go from the faculty to the student level. Student in the sense they can call PhD scholars, what you are saying that. At the same time, PhD scholars have the capability of learning these skills, developmental activities, and the new trends, updates, everything, where the guide or supervisor will also listen to them and cope up with the certain kind of a topic. Let us just take for the first topic, the electromagnetic energy. I hope 23 of them have joined, no issue. Let others get joined very soon. What meant by electromagnetic energy? Of course, the definition starting from the standard one, the people are saying that what are all those things? No need to repeat at least. But I will take up in such a way at the earlier slides or maybe beginning slides in a lighter way, where it can touch upon the concept. And the later we will see that how that strength can go. See, the same Ohm's law, whatever you studied from the high school, even at the level of the PhD also, you can have the same Ohm's law. Maybe the Newton's laws, maybe the Planck's law, whatever the laws even here we are discussed, it will never change. They're called the laws. Okay. Being electromagnetic energy, this is the spectrum what I have seen. Okay, immediately we are jumping into the spectrum they can call, no problem. Electromagnetic waves are the one, or electromagnetic energy is the one where it is composed of all sorts of energy which is available in the universe to a great extent. Spectrum is the one where you can have the spectrum. If you allow some white light or maybe any kind of a light except the monochromatic light they can call actually, through a prism where the base of the prism is at the bottom actually, it has to undergo a dispersion. It has to undergo a dispersion, and due to the dispersion, you can see the different colors. That you can call it as a wave Gaia, starting from violet at the bottom towards the red, which is deviating more, which is dispersing more. Violet and blue are dispersing more. That is if you expect that dispersion angle actually, if you expect it, okay, compared to that of the red actually. That is why even you might have seen that a PhD scholar or at the tenure of the PhD, you should have a great capability of understanding the phenomena and also having a great observations. Whatever you observe, if it appears to be different than the others, that becomes a research. If you see the phenomena as such of the others, it may not have the different views. Of course, I am not saying that you have to always having a deviation from the views or deviation from the original thoughts. Any problems, any situations, any schematic things, if it appears to be a different for a researcher, then that research can be identified, recognized, or maybe documented. Here, what I want to say is that people are seeing that every time actually, even if you stand near our, 1 second, sir, sir, namaste, sir, ತೊಗೊಂಬಿಟ್ಟಿದ್ದೀನಿ ಸರ್ ಆಗ್ಲೇ ಇಲ್ಲ ತಗೊಂಡಿದ್ದೀನಿ ಹಂಗೆ ಎಂಗೇಜ್ ಆಗಿದೆ ಅಲ್ಲಿ 25 ಜನ 26 ಜನ ಇದ್ದಾರೆ ಸರ್ ಓಕೆ ಥ್ಯಾಂಕ್ ಯು okay, for example, if you stand near this signal, traffic signal, of course, if it is switched on, actually, we'll find 3 colors. One is the red, another one is the green, and another one is the yellow color of that kind. That depends. Why they have chosen red? Why they have chosen green? Why they have chosen the yellow? It makes a sense. Makes a sense. We'll come in the discussion. Actually, did not be in deciding the traffic signal, but it is for all. While giving the text message, I told that actually we are in a place where we are underneath the some kind of a phenomena where we are submerged, we are immersed, we are exposed to all sorts of the energy and all sorts of radiation where we can't feel it, we can't touch it, we can't see it. Seeing means seeing a wall of some color, seeing a table of color, some color, seeing a chair of some color, seeing people wearing the dresses of some color are different. What is actual color has to be decided. What is the actual color should be known very clearly actually. In the sense, people are saying in such a way that colors are not actually the colors actually. Whatever the objects which are reflecting the radiation, that color, that reflection part, what we are observing as a detector on eyes or treated as one of the detectors actually can be taken as the color of that one. If you question such a way, by the end of my class, today's class actually, you'll come to know that no colors exist. They are the different wavelengths of the energy packets of a photon, or they are the wavelengths. Hello. They are the wavelengths of different the wavelengths of an energy packet actually that appears from one to the another. One to another. Want to shift it. Okay. Being this, we'll see that from the basics we studied such a way that if you allow the any visible light, preferably visible light actually through a prism, it will disperse into different colors. Are it only 7 colors which are available? That we have to see that. Electromagnetic waves are maybe the waves which are responsible for communicating through a media or between the media by some energy, or transferring the energy from one point to another point. Actually, they deal with the electromagnetic waves. With the spectrum is nothing but the distribution of the energy or distribution of wavelength, distribution of a frequency in a particular manner. We'll see in later slides in such a way how it has to go. This you might have seen actually. I don't want to give that actually. You want to get some of the slides directly from the website to convince you actually. Electromagnetic waves are nothing but the transverse waves without the medium. Transverse waves without the medium. They can travel through empty space. There's no doubt in it. Or maybe they can travel through the vacuum. Maybe at the speed of the light, what you expect in vacuum. Of course, if it is in media, certainly the speed has to come down. Transverse waves are in such a way that what is shown in the bottom picture actually in such a way, it is having more or less a sinusoidal wave where the trough and crest can happen between the two peaks, or maybe whenever it completes one cycle. Length of one wave is represented by one wavelength. Need not be always from crest to crest or maybe trough to trough, unless until it completes one cycle of about 360 degrees. You can say that this is the direction of the wave starting from left to the right, and the height of the wave can be treated as the amplitude. Okay, amplitude, and the movement of, for example, water molecules also can be taken in such a way as an example how they move in such a way that being this, it composes of the two components. One is the electric and magnetic waves. They can travel and they can also vibrate. It includes both electric as well as the magnetic component, and have some magnetic and some electrical properties to them actually. See that the top picture shows that how magnetic and electric field waves, and the direction of the propagation towards the right of its path. That's what we learned so far. Being this, when an electric field changes, because of the change in the electric field, so does the magnetic field also will change. Means the changing magnetic field causes the electric field to change. When one field vibrates, so does the other. Means if there is a vibration occurring on the electric field, the magnet that will reflect on the magnetic field, or if there is a variation in the magnetic field, that will also reflect on the electric field to a great extent. This is how that electromagnetic schematic represented here. Actually, that both E and H are the perpendicular to each other. Electric wave is represented in blue in color just to recognize, nothing to with the color actually, and the magnetic field is represented in terms of the red in color. The wave propagates, or the energy propagates towards the wall, towards the board, towards the display, they can call actually. Being this, electromagnetic waves travel very fast, no doubt, almost speed equal to that of the speed of the light, 3000 kilometer per second, they can call in vacuum. At this speed, the light can travel almost 8 times in 1 second. In 1 second, it encircles the 8 times the circumference of the Earth, particularly over the equator, keeping about 6,400 kilometers as the radius of the Earth, or about roughly about 12,800 kilometers the diameter. Energy wave acts like waves as well as particles. There is a dual nature they can call actually. Electromagnetic radiation has properties of waves, but also can be thought of as a stream of particles. What kind of a stream of particles? Stream is like almost like a bullets which are coming from a gun, that they can call stream of the particles to a great extent. For example, light, visible light they can call. Don't get mixed up with the light means the electromagnetic of that kind, visible light. Being this, light acts as a wave, there is no doubt. You can see the bottom diagram. Light behaves as a transverse waves, which we can filter using some polarizer lenses, or which we can filter using any kind of a filter in this is we can filter in such a way we can use any kind of a material to block the movement of the radiation. Even we can also use the polarizers. If you rotate the polarizer, that is the glass sheet actually they can call actually, we can abstract. Means that is, see that source is coming from us actually, it is falling on the target. This is the target part actually. Means if they are parallel to each other, it allows the entire intensity of the light to flow through. If it is perpendicular, means that is the polarizer is perpendicular to the plane of propagation of the light. Okay, that can be attenuated to a great extent, and it makes the white and the dark. It need not be spectra of that kind. What happens? Light also acts as a particles. There is no doubt in it. We can call it as a photons. For example, if you see the right side bottom diagram, when directed at a substance, light can knock the electrons or knock the electrons from an atom, and that phenomenon is known as the photoelectric effect. In general, what you expect. We will deal these effects later. Means to say that photons are the packet of energy. If the energy supplied is very sufficient, actually, certain electrons either from the outer shell or maybe an innermost shell can be knocked out. Knocked out and just removed, thereby creating the positive ions either in the atmosphere or in the material to a great extent. Being the materialistic properties, certainly they may not be knocked out. Certainly they will be moving from one point to another point, thereby creating positive ions actually. Positive ions. Being this is also, you have seen the diagram. Electromagnetic spectrum, how it looks. This is the electromagnetic spectrum is the name actually. For the range of electromagnetic waves when placed in order of increasing frequency, starting from radio waves to the gamma rays to a great extent. Increasing in frequency is nothing but the number of oscillations which can occur per unit distance they can call per meter. Okay, number of oscillations per meter, even whatever may be the lowest value you can expect actually. And the wavelength is nothing but the length of a wave in a given distance, Okay, see that from the left corner, left side actually, left extreme, the towers where it can emit the radio waves. You don't think that it is the electrical line actually. They are not of the electric line of that kind. Radio waves, then maybe microwaves where you are using the mobile phones and other kinds actually for the signals, even microwave oven of that kind, they employs the microwave, particularly in this region. Okay, as you are going towards the right part of it actually, the wavelength decreases and thereby frequency increases. Means that is the number of oscillations per second. Number of oscillations per second increases as you move towards the right part of it. Then infrared somewhere here, maybe for all hotter objects they can call. Visible light as an example of the rainbow to a great extent. Sun also emits radiation, all the category, including the ultraviolet. You may not expect that ultraviolet source somewhere other than the sun to a great extent actually the ultraviolet. It's good if it is at the greater height, at the stratospheric height, and if the same radiation, that is ultraviolet radiation, reaches the surface of the earth, it is so dangerous, and it's also carcinogenic for the thing. And the X-ray, maybe you might have taken an X-ray photograph whenever there is both cracking in bones, or maybe in identifying the faults in material, or maybe identifying the intactness of the material, or maybe the human body, particularly to a great extent. Gamma radiation, either for the exposure or maybe several applications they can use. The doctors, dentists, everywhere will use the X-rays for the diagnosis of the patient, for the intactness of the bones to a great extent. This general what we have covered so far. Fine, no doubt. Notice that the wavelength of the light starting from long radio waves to a gamma ray gets shorter. Means wavelength gets shorter and shorter. Length of the wave becomes narrow and narrower, actually get called. Or the oscillations will be quite high. Starting from 10 to the power of 3 of a meter, almost a kilometer, the length of one wave is almost a kilometer, to the extent of the length of one wave is of the order of angstroms, few angstroms they can call, or few angstroms, sometimes picometers also, picometers also actually. Means about the size, if you expect, the radio waves can expect this dimension of the building, they not be 100 meter, 1 kilometer of that kind, few meters, few tens of meters of, they can expect about 20 meters, 30 meters height of that kind. And here you'll get the human body almost about 1.5 to 1.8 meter of that kind. Maybe honeybees, small in dimensions. Still, you can go with the pinhead, protozoans, molecules of the order of about ultraviolet range of the order of about 10 to the power of -8 meter, almost 0.1, about 10 nanometer of that kind, 10 nanometer. Then the atomic level, almost of the order of angstrom, few angstrom to a great extent, with the maybe the dimension of an nucleus, and also dimension of nucleus is femtometer. Okay, maybe atom of that kind, or even atomic nuclei will start from about few angstrom to the further. What happens here, if you see the bottom panel, even the global positioning systems, GPS, what we are observing to move from one point to the another point with the earth path, measures the time it takes a radio wave can travel from one point to the another point through the satellites to the receiver, and determining the distance to each satellite very precisely. There are about 24 satellites which are revolving around the earth actually, where you can track means the GPS can be tracked actually to the precise of the few meters accuracy, even few meter accuracy they can call. They have not gone lesser than the 1 meter to a greater extent, but there are some very good high resolution sensors which are kept in the satellites, like for example, QuickBird and other things. The sensitivity goes, or the resolution goes, of the order of about 0.24 meter, or about 24 centimeter they can call. All these applications, whatever they are achieving, is by the virtue of the electromagnetic radiation. This you might have seen, I hope actually, sorry, there is no doubt in it actually. This electromagnetic spectrum, starting from either you can write in terms of the wavelength, lambda, or in terms of frequency, either nu or maybe nu you can use, or in terms of the wave number also they can write. Preferably only in spectroscopy we will use the wave number. In other disciplines, either in terms of the frequency or maybe in terms of wavelength they can specify. Starting from few hundreds of meters till to the extent of 10 to the power of -12 meter is the wavelength actually that scans most of the materials whatever we are using in our day-to-day life. Common name what we can call is the radio waves starting from about 0.1 meter to almost about 1 kilometer. Maybe microwaves covers about 0.1 micrometer, 0.1 meter to about of the order of the few millimeters. Okay, then infrared somewhere here. See the visible spectrum. Visible is very narrow band actually, very narrow band. Even bacteria, virus are of the dimensions of the few micrometers, in terms of the microns they can call. Ultraviolet radiation is having the wavelength of the tens of nanometers, and even size of the proteins of the order of about the few nano, and then water molecules and other things will come into picture. See, means as the frequency goes down, energy also goes down. Means the frequency, means waves per second is the frequency. Here, this is increasing order, higher order, this is a lower order. Energy wise, this is the increasing order. If the frequency is more, the energy is also more. Energy of a packet of photons they can call will also be more. This also can be measured in terms of the electron volts, where E is okay. Three relations you can remember. One is E is equal to h times nu, that is the Planck's constant times the frequency, or E is equal to hc by lambda, that is where you can have the conversions from the wavelength to the frequency. Nu is equal to c times lambda, or maybe hc by lambda for the energy, or even E is equal to E is equal to mc square for the particles, E is equal to h over p using de Broglie wavelength for the conversion from the duality from either it may act like a particle or maybe it may act like a wave of that kind. Means energy packets like almost like photons, electrons, highly moving, where the speeds are comparable with that of the speed of the light, acts in dual nature both. Sometimes I like a wave, sometimes I can a particle of that kind actually. The energy also measured in terms of the electron volts. 1 electron volt we can express in terms of 1.6 × 10⁻19 of an volt can have the conversions at any convenience time actually. For example, to knock out an electron from the hydrogen atom, maybe innermost shell of an hydrogen atom, they can call actually. It requires about some 13.6 electron volt, what you are expecting. Or if the energy required for a photon for the fission should be of the order of about 0.51 MeV or about 510 keV of that kind actually. Being this, let us jump to the actual topic, what we are having. Good. This is the same diagram, but it can be legibly seen actually. Here on the top, we concentrate in such a way that this is the wavelength in terms of the meters we have written, starting from my pico, even femtometer. Femtometer is 10 to the power of -15 of a meter till to the extent of the order of the 10 to the power of 10 of a meter to a great extent. Great extent actually, almost 1 million kilometer they can call 1 billion. The bottom line shows that this is the what we are expecting, the conversions from the energy reciprocal of that kind. Okay, nu is equal to c over lambda. C you can take the into 10 to the power of 8 or times the wavelength you divide, that you can get what you are expecting the frequency. Starting from the cosmic rays where the energy is quite high, this is in terms of the electron volt they have written actually. Energy is quite high of the order of 10 to the power of 10 electron volt, means to say that few giga electron volt, 10 to 100 giga electron volt is the energy range covered by the cosmic rays of all kind. Maybe the gamma rays, maybe to still maybe a little extent actually, almost 10 to the power of few MeV to GeV, few MeV to GeV. Then the X-rays comes, both hard X-rays as well as the soft X-rays. Maybe tens of MeV. Then ultraviolet radiation may not be MeV to that extent. Few keV, you can call few keV, about 100 electron volt to about 10 keV of that kind. Visible ray, it looks like a dumbbell shape, very narrow band actually, very narrow band, almost about 400 to about 750 either in terms of nanometer, or 400 to 4000 to 7500 angstrom, or about 0.4 to 0.75 micrometer, whichever way the unit, we can have the conversions you can make use of it. Then comes to be infrared, either maybe the near infrared towards the ultraviolet, or maybe far infrared, which is towards the away from the red actually, lies with about few micron to about few millimeter of that kind. But radars works almost in the energy range of few tens of meters to about a meter of the order. Your FM radio works exactly between somewhere here, the frequency about 93.1 megahertz or 100 megahertz you can expect actually. That is the frequency. We just convert into that 100 megahertz frequency into the wavelength. You'll get to know that. Then TV signals will get expect somewhere about few tens, 100 meters of that kind. And short wave maybe somewhere few 100 meters, 300 to 500 meters. One can have the broadcast starting from about few meters to almost few thousand meters to a great extent. But power lines which are transmitted few kilometers, not the wavelength to a great extent actually, power transmission can go in such a way that they can transmit from Kashmir to Kanyakumari to Kashmir to a great extent of that of about 4,000 kilometers, 5,000 kilometers of that kind actually. Still good, valid region of that kind. The bottom right corner shows that it is very much related with the either nuclear physics or maybe the phenomena which can happen in the study of the spectrum of any kind of material they can call. You can have the three more of the particles, three type of the particles also you can call, either alpha, beta, and then gamma. Alpha, beta, gamma, they are the particles. Alpha are nothing but the doubly ionized helium nuclei. Beta are either the electron or proton, electron of that kind, electron or proton of that kind, and the gamma is the radiation without having charge, one doesn't have a mass like photons of that kind. We expect that the penetration power or maybe the ionization power, penetration power is nothing but how far they can travel through a media, either maybe in a piece of a paper or maybe in wood materials. Don't take it as a log of the larger one. It will be considerable, that few millimeter to few centimeters of that kind. Maybe a concrete slab of the order of about few millimeter to about few centimeters, even sometimes few tens of centimeters they can call. Maybe a brick wall of about some 20 centimeter to 30 centimeter of that kind. Alpha particles are stopped by a piece of paper. Piece in the sense a thickness of a paper of the order of about maybe 10 micron to a greater extent actually, where the ionization is quite high. Means they can ionize. If their ionization is quite high, beta particles can be stopped maybe over a wood. Maybe gamma rays still they can travel piece of paper, wood, and all materials. Maybe they can go ahead in such a way that the concrete slabs or maybe lead shields are good enough to block or to stop the radiation which is passing through by the gamma. In other words, stopping energy is nothing but how much they interact with the material, how much they interact with the matter to a great extent. If they are passing through without interacting, means there is no interaction possibility. Interaction cross section is very weak or minimal to a great extent. If they are interacting, in the sense they will spend a lot of time with the molecules of the detector or target, they can call either the way target, and where they will lose the energy to a greater extent in the interactions by colliding with the molecules or maybe the atoms or the electrons or maybe all together put together, and thereby losing their energy or transferring their energy to the molecules and becoming and will be trapped and will be trapped. This is alpha particles will be trapped with the paper. Maybe beta particles can be trapped, of course, maybe few millimeter wood and gammas, of course, though both of them can't stop, they can go. X-rays, for example, still they can go, there is no doubt actually. Means to say that even though some of the things are not visible for visible light, they are visible for X-rays, they are visible for ultraviolet, they are visible for gamma, they are visible for gamma, cosmic rays actually. Such a way, even if there is a crack in our bone, either maybe whichever may be the part of the body except the brain, doctors will suggest for the X-ray. Why can't they see directly through naked eye and they can analyze? They can't, because the visible light will not pass through the human body or maybe any of the material. But if you allow the X-rays, certainly they will pass through. Wherever the cracks are there, wherever maybe the cavities are there, maybe to a great extent, if there's a cavity in the sense, don't expect that of a few meters or few centimeters of that kind, maybe a minimal value of maybe of the micron level to the millimeter level, still those faults, those defects can be identified either maybe from the human body or from the material, doesn't matter. Means why X-rays are there? Means if you allow the X-rays, you can see that the picture clearly in a spectrum developed either over whichever be the kind of a plane, but we are expecting. But if even though it is invisible for the visible light, it is visible for the X-rays, it is visible for the gamma rays, it is visible for the cosmic rays to a great extent. But in terms of the wavelength, what happens? As you move towards the higher energy, wavelength decreases and the energy increases to a great extent. Being this. Okay, we are coming to the hardcore right now, that's fine. What's the electromagnetic spectrum in general they can call? On the right side, you can see the diagram starting from the bottom till to the top. Of course, these are the different versions of representing the same picture. Of course, researchers will do that. Researchers will like that actually. Even the same Ohm's law can be written by 500 times different way, not with the number, what I want to say that 500 times, 1000 times in a different way, the way you are expecting, the way you are feeling, the way you are conceptualizing actually. What happens here? The electromagnetic spectrum is nothing but spectrum is the range of all types of electromagnetic radiation, starting from either you can use the gamma rays to the radio waves, or it can swipe from gamma rays of the higher energy and the lower wavelength, or maybe the higher frequency to a higher wavelength, or maybe the lower frequency, or even to the lower energy of the radio waves to a great extent. Radio waves to a great extent. Means radiation is the energy, electromagnetic radiation is nothing but the energy that travels and also spreads out as it goes. How? It is visible light, we can call them as a visible light if it comes from the lamp, okay, if it comes from a candle, if it comes from a campfire, if it comes from any of the fire of that extent, okay, visible light where you can expect somewhere here, actually, somewhere here. Okay. Then that can also be treated as the radio waves, which are coming from the radio stations when it was telecasted. They can call either FM radio or maybe AM of that kind, or maybe both together, either from Mysore station or maybe Goa stations or maybe Kerala, or even you can have the some kind of an amplitude modulated stations from Sri Lanka. They can call earlier. They used to do that. Nowadays, the radio usage of the radio has stopped. Only the FM is still it's in use. We don't know how long it can continue to a great extent. There are two types radio waves coming from the radio station are of the two types. For example, these are the two types. In this sense, visible and radio waves. Visible and the radio waves are the two types actually. Other two types are the electromagnetic radiation that make up the electromagnetic spectrum are the microwaves. You can see that here. Microwaves, maybe microwave oven is used for cooking, so many things. Or infrared light, actually, infrared light, even ultraviolet light, which is coming from the stars and sun. X-rays, which are emitted, are even artificial, and the gamma rays. What it shows, the image here, what we have shown on the right side, might encounter each portion of the electromagnetic spectrum in our day-to-day life. That is why I quoted in the beginning, or maybe texted in this message, just to make a curiosity for you to join for the class. Of course, it is a mandatory for you not to skip. There is no doubt. Of course, if you are capable of reading yourself and if you are capable of going through the material yourself, it should not keep. The attendance should not be kept mandatory. Actually, okay, you'll not to see. Sometimes some researchers will feel that in such a way, rather than attending the classes, if I spend the same time for the reading or something else, that may be a good idea. There is no doubt in it, actually. What it says is that actually we are underneath of all kind of radiation, actually. All kind of radio waves, electromagnetic radiations, microwaves, then visible light, infrared light, ultraviolet may not be that extent. X-rays we don't have. Occasionally we can have the exposures. Gamma rays of all the kind, certainly we can have the exposure actually, starting from 4,000 angstrom to about 8,000 angstrom to a great extent. Being this, let's see that bit by bit. Radio waves are radios in the sense the devices which are used for hearing or receiving the signals, for example, radio signals, captures the radio waves which are emitted by the radio stations, bringing your favorite tunes, either songs or programs, what you can expect. These radio waves are also emitted by stars. There is no doubt in it. And gases in space, remember. Now, the complexity goes, depth-wise it goes. Whatever you are thinking of electromagnetic radiation, either one or two slides or maybe first few tens of slides actually, has to deviate. Radios captures the radio waves, no doubt in it. At the same time, the stars are also emitting the radio signals. The gases in the space did not be. Why gases in the space? Because near to the surface or maybe in our ambient atmosphere, what we are living, the density is so high, or the pressure of the atmosphere is so high, pressure of the media is so high, it does not allow for the interactions between the molecules. Mean free path is so high, immediately it will capture to its neighboring molecule. If you go to this space, you can find the isolated particles. Maybe those individual particles may be separated by few tens of kilometers to about few hundred kilometers to a great extent. Certainly, you can have these type of features. How that energy is emitted, that we'll see later. Okay, radio waves are also emitted. These stars are also emitting the radio waves. Various gases in the atmosphere also emit the radio waves to a great extent. If you are having a receiver to receive, including the transmitter, which is transmitted by the radio, it should not have any interference. That sometimes you might have seen that while tuning the radios, while tuning your devices, you may be able to receive some other kind of signal. You may be calling it as a noise, you may be calling it as an unwanted signal of that kind. Unwanted means neither the tunes, nor the music, nor the programming things, actually something else. That different electronic circuitry has to have a filtering concept, filtering in the sense filtering off or reducing off such type of noises and extracting the signal what we want actually. Okay, we are under the ocean of, not in as in the water body alone, we are under the ocean of the entire radiation. The second did not be the same order, maybe decreasing wavelength they can call actually. Okay, after this, then AM radio, then maybe an amateur radio they can call olden days. Microwave radiation will cook your food, no doubt, either whatever you want it actually. Even you can warm up either a cup of coffee or maybe tea or milk, or even toast it actually. Toast any kind of material in just few minutes, but all this is also used by an astronomer to learn about the structure of nearby galaxies. Don't think that actually. Microwave is good enough. The same radiation what the microwave emits to heat up, to warm up the food in your dining table or in your dining room or even in your kitchen or even your laboratory. It is good. Let us keep the microwave ones in all your laboratory where you can work from morning till midnight. What you can expect. Okay. Thing is that the same galaxies which are emitting the microwaves means they will call it as an CMBR, cosmic microwave background radiation. They can call actually CMBR is nothing but cosmic microwave background radiation. We are under the influence of that. We are not alone. We are not isolated. We are not single. We are not independent of that kind. Actually, we are in a system. We are in a system. Galaxies emits the microwaves. And night vision goggles, for example, pick up the infrared light, there's no doubt, which are emitted by our skin. Our skin also emits the infrared. Any object which is at any temperature, higher temperature, above 0 degree Kelvin, they can call, 0 degree Kelvin, must emit certain kind of radiation. That radiation is known as the infrared. Means any object, if it is need not be maintained, if it is at a temperature greater than 0 degree Kelvin, certainly emits infrared. Okay, but also emits the objects with heat. In space, okay, above the atmosphere, they can call, infrared light helps us to map the dust particle between the stars. Okay, there are so many stars in the night time. You might have seen actually through your naked eye without using any aid. Of course, you can use the telescopes also. There is no doubt. Okay, but thing is that without that also, or your binoculars to a great extent, you can see the nighttime sky, preferably from the rural areas if you are going away from your village, or maybe if you are taking rest on the upstairs. Actually, certainly you can see the night sky watch, they can call, where you can see the plenty of stars. Plenty means at most about 6,000 to 7,000 stars can be viewed by a human being in a hemisphere. Actually, to a great extent, they also emit the infrared light, which that helps us to map the dust between the stars. Our eyes can detect visible light, no problem. Flies, there are flies, you might have seen that actually, light bulbs, maybe of any kind, and also stars, which all emit the visible light. Very narrow band, about 4,000 to 7,500 or about 8,000 angstrom of that kind. Ultraviolet radiation, which is emitted by the sun, and are the reason for the skin tans and burns actually, thanks to the atmosphere. Without the atmosphere, those radiation might have reached the earth. They are near the surface of the earth actually, thereby creating the skin tans or maybe the burns. Hot objects, for example, in the space, emit the ultraviolet radiation to a great extent. Where within this region. Still, if you go down, a dentist can. Sunil Kumar, Sunil, mute. Sunil. Sunil Kumar, mute yourself. Okay. A dentist uses the X-rays to image. Of course, it is not advisable to go for as many as X-rays for the human beings. And airport security also uses them to see through the bag. Through the bag what the content is. Hot gases in the universe also emit X-rays, for example. Okay, but there are plenty of studies where you can use the X-ray diffractometers to study the properties of the material in material science and the condensed matter and the classes. So many groups in our department are utilizing the X-rays for the analysis of the material, characteristic properties of the material to that extent. Doctors use the gamma rays imaging like therapy. Okay, radiation therapy also is there. Imagine to see the inside of the body. The biggest gamma ray generator of all is the universe. Universe is one of the biggest generator of the gamma radiation. It all terrestrial gamma rays and terrestrial flashes they can call. This is the lightning activity which flashes in a micro to nanoseconds level, and where produces a current of the order of several million to gigawatts and of the power, and the discharge of the electricity is quite high actually. Being this is a radio wave is same as that of the gamma ray, that you have to think it of because you are in research mode. Are radio waves completely different from physical objects than the gamma rays? No, it's not of that kind. They are produced in different processes. Radio waves are produced by some way. Gamma rays also produced by some way and are detected in a different ways, but they are not fundamentally different. They are all the same. All kind of radiation which belongs to the electromagnetic radiation, starting from gamma rays till to the extent of the radio waves, they all have the same properties. Same properties. Same and similar are different. Same means same in the sense the way in terms of either wavelength, in terms of the energy, or in terms of the frequency, or in terms of their penetration. Maybe something may be more, something may be less, but as a basic and fundamental property is considered, they have to obey all the criteria, they have to obey all the rules, they have to obey all the laws guided by the nature. That we'll see later. Radio waves, even gamma rays, visible light, and all other parts of the electromagnetic spectrum are having the electromagnetic radiation. Okay, this electromagnetic radiation can be described in terms of the stream of massless particles. They can call it as photons, not phonon. Remember, it is a photons. Each are traveling in a wave-like pattern at the speed of light. At the speed of the light. Each photon contains a certain amount of energy. Okay, and the radiations are defined by the amount of energy found in the photons. Some photons of the order of million electron volt, you can say the energy. Some of them are in the kilo electron volt. Some of them are in giga electron volt. Some of them are only electron volts. Therefore, radio waves have the photons with low energy, shorter wavelength they can call, longer wavelength they can call. Okay, and microwave photons, which are having a little more energy than that of them as the radio waves, but infrared still they are having a more. If you are coming from right to the left, the energy increases. Infrared photons have still more than the visible, than the ultraviolet, than the X-rays, and most of the energetic particles are the gamma rays. Here you can remember here X-rays and gamma rays. Gamma rays are the highest energetic particles are available in the universe. Visible spectrum is very light minded thing. Now the technique comes. How to measuring the electromagnetic radiation, how one can able to measure. Now just you see through your naked eye, either the bulb is glowing or not, tube is a switched or not, or incandescent bulb is on or off, or LED bulb is on or off. That is enough. That is one of the eyes are a good detectors to detect the electromagnetic radiation, particularly in the visible region. Don't bring the two words together, particularly visible region. Invisible, there are so many things. Even though it is invisible for human eyes, may be visible for some other creatures, some other type of detectors. Electromagnetic radiation be expressed either in terms of the energy or wavelength or frequency, that you are well aware. Frequency is measured either in preferably in seconds per second or in hertz. Wavelength is also measured in meters. Energy is measured in electron volt. Of course, you can have the conversion from joules or maybe calories or maybe different thing actually. This energy they are saying that particularly the electromagnetic energy they can call. Electromagnetic radiation or electromagnetic energy is measured in terms of the electron volt. Each of these quantities, three in the sense, forget about the last one actually, either maybe the energy or wavelength or frequency quantities for describing the electromagnetic radiations are related to each other with a precise mathematical way. E is equal to h nu, E is equal to hc by lambda, E is equal to h over p, de Broglie wavelength, duality of that kind. But why have these three ways of describing the things, each with a different set of physical units? Some of them are with the energy, wavelength, frequency. Why? Because the scientists don't like to use numbers any bigger or any smaller than they have. I'm having a hand with 5 fingers. I'm having a 2 hands with 10 fingers. Some of them less, unfortunate. Some of them still more fingers, maybe. I don't know, maybe from your fraternity. 1 or 2 additional fingers. This is a grace. Okay, but I can't count beyond that limit. We don't. Scientists in general, they don't want to use the bigger numbers. They don't want to use so smaller numbers. What normally they would do? It is much easier to say 2 kilometers than to say 2,000 meters. That is the problem. That's why the conversions will come into the picture. Generally, scientific community uses the units that are easiest for the type of electromagnetic radiation they work with, either in visible spectrum or the spectrum which can domain within the visible or maybe the ultraviolet, or maybe with the radio waves, or maybe with the gamma radiations, or maybe the X-rays of that kind. Now, as a specialized thing, giving the example for this whatever I am teaching is linked with both astro as well as the atmospheric science. In fact, in the space, in the planetary physics, in the space physics, in the astronomy, you will find the innumerable number of examples and also a complexities involved. It is not a one-dimensional program of solving something like that, which is having a direct link or direct hint of that kind. What normally they have to do, let us see that the second half of that. Astronomers who study the radio waves tend to use the wavelengths, okay, fine. Sometimes otherwise the frequencies to a greater extent. Most of the radio part of the electromagnetic spectrum falls in the range from about 1 centimeter to about 1 kilometer. Almost, if this convert the distance into the frequency, that lies to be about 30 gigahertz to about 300 kilohertz in frequencies, and a broad part of the electromagnetic spectrum. And infrared and optical astronomers generally use the wavelength, the same case. Infrared astronomers use the microns for wavelengths, ranges from 1 to 100 microns. Optical astronomers use both angstroms and nanometers, both together. Of that order they can call. Optical astronomers in the sense they are using the optical telescope to a greater extent. Infrared astronomers means where they are using the detectors of in the domain of the infrared radiation for the detection. Like this, like violet, blue, green, yellow, WIB-GIAR, what you are expecting, have the wavelength starting from 400 to 700 nanometer, 750 doesn't matter. This range is just a tiny part of the electromagnetic spectrum. Which range? WIB-GIAR, what visible we are calling. So the light of our eyes can see is just a little fraction of all the electromagnetic radiation which is surrounding us or which is around us, existing around us. Wavelengths of the ultraviolet, wavelengths of the X-rays, and wavelength of the gamma rays of the electromagnetic spectrum, all very small. Small in the sense it is a relative terminology, okay? Because 10 is smaller than the 11, then 0.1 is smaller than about 1 actually. It is a relative terminology. Ultraviolet radiation falls in the radiation in the range from few electron volts to 100 electron volts, and X-rays maybe 100 eV to about 100 kV. But gamma rays, what happens? They are having the photons with energies greater than 100 kV, or the energies almost lies from 1 MeV, from million electron volt to of the order of plural giga electron volt to tera electron volt. That kind. Being this, see a beautiful spectrum. Most of the electromagnetic radiation from the space in the sense above the atmosphere have to go, because atmosphere acts like an obstacle. Earth's atmosphere preferably. Earth's atmosphere acts like an attenuator. It is an obstacle for the astronomers. That is why our Dodmani sir always says KN is always an obstacle for him. Means for him is for his observations, where we are handling with the atmospheric studies, but they are handling with the astro and space physics at the same time. If you know if you understand the atmosphere in a proper way, that makes the boon for the astronomers at what time, at what point, and at which place the observatories are good enough to understand the phenomena. See that here, this is the height wise as you go up, atmosphere exists up to about 100 kilometers. Then beyond that, nothing. Where the satellites are revolving in the thermosphere and above thermosphere, that kind. Optical window will fall somewhere here between ultraviolet to the infrared. The red color above violet is called the above red is called the infrared, and below violet is called the ultraviolet, and then ultraviolet WIB-GIAR of that kind actually. Red color is mainly because the wavelengths are quite larger compared to the that. Okay, here energies are higher here actually. Well, what happens here? Most of the radiation, electromagnetic radiation from the space, is unable to reach the surface of the Earth because radio frequencies or visible light and some ultraviolet light makes it to sea level. Up to sea level they can come. But astronomers can observe some infrared wavelengths by putting telescopes on the mountain tips. You can see here actually mountain tips, they can observe some ultraviolet radiation, maybe at a height of about 8 to 10 kilometers from the mean sea level, not from the surface level, from the mean sea level. Radio wave spectrum, they can observe to a great extent, they can pass through. High wavelength radiation which is having higher wavelength, can easily penetrate through the atmosphere, and reaches because of the larger wavelength. High energetic particles which will be trapped with the interactions. This we'll learn later, or this we'll discuss later actually. What happens because of this? Long-term observations, it is best to have a detector on an orbiting satellite here and get above it all, whatever it is happening. Means for long-term observations, or maybe for having an observations of the space, observations of the stars, observations of the galaxies, observation or any phenomena need not be of that kind. A detector which is kept in an orbiting satellite at a height above the atmosphere, to see whatever we want to see beyond that limit. This is an ideal place. Being this, how do we know what we know? We know that we understand the electromagnetation, but we should know that how do we know that what we know actually? Whatever we have come to know should be known. See on the right extreme top, okay, a beautiful picture of the rainbow. Either inward or outward, you see that there are varieties and different types of rainbows actually. Astronomers have to rely on light, and astronomers have to rely on the electromagnetic radiation or properties of the electromagnetic, which is coming from distant objects in the cosmos. Since we can't visit these objects in our lifetime, the neighboring celestial body, the immediate neighboring celestial body is the moon, that they can call it as an artificial satellite of the, natural satellite of the Earth actually, is at a distance of about 3.8 lakh kilometers, 3 lakh 8 kilometers. Even if you send a signal, it will take roughly more than a second to reach. Only to reach, and then to come back, another. Means it requires minimum 2.5 to 3 seconds to get back the signal, what we are sending from Earth, if it goes to the moon and goes back and telling the information that what moon is made of, what moon is composed of, what is the structure of the moon, not the interior structure, maybe the exterior also, maybe the exterior, maybe the interior, that is a different way actually. Okay, yes, like that. If that's the case, even if you want to go to the nearest planet, moon, Mars, it's about 75 billion kilometers. Spacecrafts have taken 10 months to reach the Mars without stopping actually, because we are all missing the buses, we are all missing the trains, we are all missing the aircrafts. Whenever we want to reach in time, we may not make it actually. But if the scientists send the satellites to the neighboring orbits or maybe neighboring celestial bodies, either to the moon or to the Mars, they have succeeded. There's no doubt in it. They know the orbital mechanics well. They know the classical mechanics well, how to put a satellite into a fixed orbit, or how to put a satellite into a neighboring celestial body to see either maybe an orbiting satellite or maybe a landing. So fine, no issue at all. India is also one of the pioneering country in the space technology and also in space science to have the ventures to a great extent. Okay, the second statement says that a spectrum is simply a chart, nothing but you can see that the bottom actually simply a chart actually, or maybe a graph. Need not be a two-dimensional graph of putting some points and connecting those 2 points with the continuity, what you are trying for, an maybe either by I by V characteristics, or maybe a simple pendulum, or maybe an oscillations, or maybe the time graph, or how the temperature changes over a day. They're all the two-dimensional graphs of that. Here it is a continuous spectrum actually, continuous. Means if you plot either with reference to the frequency, or maybe wavelength, or maybe energy, with reference to the amplitude, you can see that starting from red down left extreme to the red, then maybe an yellow, then maybe green, then maybe blue, and then maybe an violet to a great extent. Have you range of energies? That's all. Meaning either it shows that the intensity of the light being emitted or the range of energies. Waveguide is also some kind of that kind actually. Have you ever seen a spectrum before? Yes, there is no doubt. There is no probable actually. because if it is for school children, actually we can say that sometimes maybe yes, sometimes maybe no, depending on their level of the classes. But as a postdoctoral program, certainly have assessed this so many spectrums, so many spectrums. Nature makes beautiful ones. We call them as the rainbows. It is also one kind of a spectrum. What we are expecting in the first slide, the electromagnetic spectrum, which can be seen in the laboratory. If you allow the white light to pass through a prism, due to the dispersion, you can see the Vipkaya, the 7 colors, manifestation of the nature, they can call. At the same time, in the nature, see that artificially can have the infinity. But can you see, can you expect that the rainbow can be seen by all at a time? No. Even though over Bangalore, for example, even though maybe in Ramnagara, or maybe in Chatpatna, or maybe in Goribidinur, or maybe in Ooty, people staying there, maybe only one kind of this, only few people can see the rainbow. It is not, it is a direction dependent, what I want to say that. It is a direction dependent. It is also a property dependent. It is also lies with the direction the light falls onto the atmosphere, and the light in which the light gets either diffracted or maybe reflected or maybe undergoing a dispersion, because of the existence of the tiniest and the tiny particles, either maybe a dust or maybe water molecules or maybe the clouds to a great extent. Okay, fine. Sunlight here, which spreads out to display its various colors. See that here? How many? You can count. Okay, you can count 7 colors. Sometimes we are misstated by our own faculty members. So our own faculty in the sense as a teachers we can call actually. It has to vary from the level to the level. Even though you are calling it as only the 7 colors, how many colors are there? Is it only the 7? Just you'll get to know the answer in another 1 or 2 slides. Spectroscopy can be used, very useful, or maybe can be used, or it is also very useful in helping the scientists to understand how an object like a black hole appears, how a neutron star exists, or active galaxy that are producing the light, of course, electromagnetic light, they can call electromagnetic radiation, how fast it is moving, means these all of them, and what elements they are composed of, can be understood, can be studied by knowing only the electromagnetic radiation which were received from those objects, either directly as a source or indirectly as a reflected beam or reflected energy. Means to say, spectra can be produced for any energy of the light, from low energy radio waves to very high energy gamma rays. Means each spectra holds a wide variety of information. Each spectrum is having its own uniqueness in revealing the information about the material characteristic, either in the laboratory of some samples or maybe the universe. For instance, there are many different mechanisms by which an object like a star can produce the light. Something with the thermal activity, thermonuclear activity, something with the nuclear activity, something with something else. Each of these mechanisms has a characteristic spectrum. That will see that. How this characteristic has to go. Maybe this is the looks like repetition. Maybe the atomic nucleus is having some kind with the wavelength of this kind, water molecules. Maybe what you expect is the virus to a great extent, blood cells, pencil lead of the order of a few millimeters. Then maybe the ladybug they can call bug, okay, a few tens of millimeters they can call. Maybe human beings about 1.5 meter to 1.6 meter space float, and the Statue of the Liberty within the ladybus. You can see the next diagram. What happens? There are different types of the spectra, maybe a continuous, maybe a emission spectra, and also an absorption spectrum together to a great extent. What happens if it is continuous? There is no break, there is no discreteness in such a way that actually starting from wave Gaia, okay, you can expect actually if we allow the white light to pass through the spectrum, it has to undergo dispersion and produces the colors, different colors, 7 colors you can expect. This is the one you can see discrete. This is a band spectrum. This is the line spectrum of that kind actually. Bright lines either in red or yellow or blue to a great extent here, somewhere with the pink of that kind. Here absorption lines, or you can also call them as the dark lines. Something gets absorbed actually. Okay, here you can expect something. What happens here? Each element in the periodic table about 118 elements right now. I don't know, maybe you have to update every day. Otherwise, you will miss some of the elements which were introduced by the mankind as an artificial elements, not be natural to a great extent. Okay. Because if you refer the books which were written in 2000, and if you refer a book by 2021, maybe some of the elements might have added in the recent books. That's the thing. Each element in the periodic table can appear in gaseous form and will produce a series of bright lines which are unique to that element. Hydrogen is having some peak, helium is having some peak, silicon is having some peak, gold is having some peak, and maybe uranium is having some peak, Neptune is having some peak, either in gaseous or maybe the elements. They have to produce peak. No two elements in the universe can have the same peak at all. Means to say that it is very easy, it is the boon, it is a gift of a nature for the mankind to identify the different elements. No two elements are looking alike. Means to say that hydrogen will not look like helium, which will, it is not like an siblings, it is not like an twins of that kind. Actually, hydrogen will not look like helium, which will not look like an carbon, which will not look like an iron. Nothing in the universe look like a hydrogen. Nothing in the universe else element look like an hydrogen. Hydrogen does not look like another element. Any of the other element can never look like a hydrogen. That is why astronomers can identify what kinds of stuff are in stars, whether they are made up of iron or gold or maybe silver. You might have seen from the news in such a way, if they are very curious to know that some of the asteroids are coming to hit the earth where they are made up of a gold. Even if you capture one of the asteroid, that may be in size of the dimensions of the huge Himalayas of that kind, boulders of that kind actually. Okay, stars from lines they find in stars spectrum. Line spectrum they can call. Study is called the spectroscopy and is so sophisticated. Okay, each element in the periodic table can appear in gaseous form and will produce a series of bright lines which are unique to that element. Maybe during Vivavos of your seniors, you might have witnessed the different spectral lines they have shown for identification of some of the elements, particularly the metal science to a great extent in our department. Our department is having more strength with the metal science. Hydrogen will not look like helium, which will not look like carbon. Thus, astronomers can identify what kinds of stuff they are in the stars spectrum. Being this, from spectral lines, one can determine not only the element, not only the existence of the element, but one can also identify what must be the temperature of the star, what must be the density of the star, which is what kind of a material it is made up of. The spectral lines also can tell us about any magnetic field of the star. Okay, means whether they possess the magnetic field or not, what kind of a magnetic field they possess, how much the magnetic field they possess. The width of the each line can tell us how fast their material is moving. You might have well known the concept of the Doppler shift, whether they are approaching the observer, whether they are moving away from the observer, whether they are reaching towards the detector or whether they are moving away from the detector. We learn about winds in stars from this. Okay, stars are nearby, not nearby. They are far, far away from it. How much away? Think it of. The light, that is the electromagnetic radiation, which is coming from the sun, takes 500 seconds to reach the earth. Okay, the same light takes almost 10 astronomical units to reach the Neptune or maybe Pluto. Okay, other stars, nearby stars, Alpha Centauri, it should be far away from that. Yeah. If lines shift back and forth, okay, which reveals that stars may be orbiting another star, because they are bound to each other. If it is orbiting another, certainly it has to emit the radiation like back and forth of that kind. One can estimate the mass and the size of other stars from this concept, neither taking a spring balance nor taking a dual balance, neither be having something like that. You can't go to another planet and take the measurement of a planet, and you can't take the measurement of a mass of a planet of our own Earth by standing on our own Earth. There are different techniques in different techniques which can be capable of. With different techniques here in terms of the electromagnetic radiation. Actually, if the lines grow and fade in strength, then it reveals about the physical changes in the star. Spectral information or the electromagnetic spectrum can also tell us about materials around the star. This material may be falling onto a star from a donut-shaped disk around the star called the accretion disk, they can call. We are about 5 accretion disks of that kind for the Earth is considered. These disks often form around the neutron stars or maybe black hole. Don't get mixed with the astronomical words, but thing is that we are concentrating for the electromagnetic radiation to a great extent. The light from the stuff between the stars allows the astronomers to study the interstellar medium. This tells us what type of a stuff fills the space between. It is not an empty, it is made up of something else. Space is not empty at all. There is lots of gases and dust between the stars. Therefore, spectroscopy is one of the fundamental tools to study the universe. If you are not understanding the spectroscopy, don't put any effort to understand the universe. The top here I have shown the same thing. Fine. Good. We are coming to everything. This is, even though it is general for electromagnetic radiation, one has to say that. I took this as the example merely because these examples convince me first to understand the phenomena that also I'm trying to convince you. Okay, see the right, how the sky can be seen in different ways. Sky can be seen in different ways. In this is, can you expect that the sky will be sometimes blue, sometimes green, sometimes yellow, sometimes red, sometimes black, sometimes white, sometimes something like that? No. While saying the colors, you will say only the 7 colors. Fine, there is no doubt in it. We'll see. Starting from gamma rays, if you observe that in the gamma radiations, how it looks. In the X-rays, this is the second picture from the bottom. Then maybe in the optical visions, maybe during only the nighttime it is blown. Daytime, you can't expect the optical observations. Maybe infrared, only in terms of the temperature of the stars, dust, and other things. This is the emission of the radio waves one can capture. This wavelength is called the multi-wavelength astronomy. Means spectrum, what we are, sorry, detector, what we are keeping to detect such type of things is multi-wavelength. Our universe contains objects that produces a vast range of the radiation with wavelengths either too short or too long for us to see. So, some astronomical objects which can emit mostly in infrared radiation, others mostly in the visible, somewhere here, okay, somewhere here, and still others mostly in the ultraviolet radiations. What determines the type of an electromagnetic radiation which is emitted by an astronomical object? Is that what determines? What determines the electromagnetic? Why the electromagnetic radiation has to be emitted? Why electromagnetic radiation has to come out of an object, of a celestial body? Is mainly because of the temperature of that body. Depending on the temperature, you can expect that what kind of an electromagnetic radiation is coming out. You might have seen that Wien's displacement law, lambda m times t is equal to some constant. That we'll see later, actually, not in this slide. What it says actually here, see the bottom diagram. This is the increasing in frequency or maybe decreasing in wavelength. Means if the frequency goes down from reddish to thickening, then what happens to the temperature? Temperature of the order of 1K, 1000 degree Kelvin to about 100 degree Kelvin, 10,000 degree Kelvin, 10 million Kelvin, 10 million degree Kelvin, they can actually. This is the temperature of the sun, interior of the sun. Exterior of the sun is of the order of about 5,000 degree, 6,000 degree Kelvin to a great extent actually. That is why it is emitting the visible light. Okay, if you go to different parts, certainly it is having a temperature dependency you can expect. Means you are studying so much of properties where depending on the temperature, how you can see the properties of the material characteristics actually. The same good example is that water at room temperature is in the liquid form. If you take it to the below zero, sub-zeros, it becomes a solid. If you take it to a relatively higher than the 100 degrees Celsius, it goes to the vapor state. Whereas oceans are the best examples for the 3 phases of the water, either in the liquid form or in the gaseous form, which are evaporating from the water body. Sometimes it goes to the zero, it becomes the icebergs of the solid water, they can call solid phase of the water, they can call. Means a solid contains the molecules, there is no doubt, and also atoms that are in continuous vibration. Means inside a gas are molecules, there are innumerable number of molecules that are flying about freely at high speed, continuously bumping into each other and surrounding matter. Thereby, with the collisions, with the interactions, energy of motion of molecules or atoms produces the heat, means transfers to the heat. The hotter the solid or maybe gas, the more rapid the motion of the molecules or atoms within that solid atom. Otherwise, if we expect that Brownian motion is quite large for the gaseous molecule, certainly it should be hotter, relatively hotter. Means temperature is a measure of average energy of those particles. Temperature is a measure of the average energy of those particles. If it is maintained at some temperature, they vibrate, they collide, they generate the electromagnetic radiation. That electromagnetic radiation travels thousands, millions, billions of kilometers in space without without losing its energy, much energy. Of course, it interacts with the matter to a great extent. If we receive such energy, one can identify what the universe is made of. Right? There exists a relationship between temperature and EMR. It's only one tabular column. We can see that. I am sharing all these PPTs to you. I will share my drive. I'm keeping this in my drive actually. Gamma rays, the temperature is more than 10 to the 8 Kelvin, starting from pulsar to the neutron stars, even accretion of the days, then around the black holes, interstellar clouds, the X-rays, regions of hot regions, maybe shock gas, neutron stars, so many. Need not be restrict your studies. X-rays need not be the restriction of the lab, which is maintained by our fellow colleagues in our own department. There are n number of sources, ultraviolet radiation, either from supernova or maybe hot stars, even quasars, visible light, preferably from the stars, galaxies, nebulae, even your own filament in your home, infrared radiation, any stars, cool stars, forming stars also having this research, interstellar dust, planets, comets, asteroids, less than 10,000 degree Kelvin, 10 degree Kelvin, not 10,000, less than 10 Kelvin, degree Kelvin, radio waves like almost cosmic background, scattering of the radiations, so many things. This is the courtesy by the NASA JPL lab. It's good. What it says? What are all the techniques which are available for us? What are all the things? It is not an easy job. It is not an easy way just to see the bulb and see that what must be the intensity of the bulb. Maybe relatively you can say that either more intense or less intense. Just to see outside, just to see the room, you can say that something is red in color, something is blue in color. It is not identified. Astronomers use number of telescopes which are sensitive to different parts of the electromagnetic spectrum to study the objects in space. Okay, of course, in laboratory also you can study. There is no doubt in it, but in a close even though all light is fundamentally the same thing, the way that astronomers observe light depends on portion of the spectrum they wish to study. What you are expecting here on the top, so many satellites which are revolving. It is only to see few. The photography is from the NASA to a great extent. See that at the band here, gamma rays to the ultraviolet. Violet means ultra means above the frequency of the violet, visible, IR, infrared, microwave, radio waves. What you can see here on the down is the ground stations to receive the signals which are emitted by the objects. Okay, different detectors are sensitive to the different wavelengths of the light. No doubt, if you send a signal in the visible, that may not detect the ultraviolet, that may not detect the radio waves. If the detector is made up of means is suitable for the radio waves, may not detect the visible at all to a great extent. In addition, not all light can get through the Earth's atmosphere. All light will never pass through the atmosphere to reach the surface of the Earth. Most of them are gets blocked. If that doesn't block, we may not live our life on Earth actually, either due to the magnetosphere or due to the corona, or maybe not corona, either due to the magnetosphere or due to the stratosphere or maybe to the rest of the part. I will let you know later actually. In addition, not all the light can get through the Earth's atmosphere. So for some wavelengths, we have to use telescopes aboard the satellites. That is why if it doesn't reach, means we have to see, we have to study actually. We want to know. Means keep the satellites in the atmosphere, above the Earth's atmosphere, certainly, to see them. The way we collect light can change depending on the wavelength actually. Okay, you might have witnessed while seeing you might have brought several TVs, particular displays they can call. LED displays fine, whichever way the angle you can see the same thing. Some CRT TVs, if you are seeing from the LCD displays, if you see from either direct 90-degree or maybe with the inclination, with the angle of inclinations, the view also will change to a great extent. These now with the represented the observatories with the HESS, they can call one of the observatory HESS and Fermi and Gemini, Newstar, Karma, Greenback, VLA. These are all the observatories actually. Okay, Sophia with the aircraft. Okay, these are the satellites actually. Fermi, Swift, Chandrayaan-2, Chandra, Newstar, Galax, Kepler, Hubble, Spitzer, Planck, Spectre, that Herschel, that kind. Okay, are all red, and this is to understand the universe. Okay, through the electromagnetic radiation. Why? Because what happens? Some scientific thoughts, for example, what size we are getting out of it actually. What is the basic twist? What is the basic? What we can not basic actually? What is the main gist of a human being to understand the universe or the nature actually? How did our universe begin? And how will it end actually? Okay, if we want to know how it begins, certainly we will want to know that how it will end actually. When it will end is a different actually. At least how it will end through a spectrum. What is dark matter? That one has to see that. How did we know that the structure in the universe evolved in a different manner? It looks like a cubic cell, what the condensed matter people or maybe the solid state community from the solid state physics can have the structure of the different structure or the properties of the different different elements they can call actually. How do massive black holes grow? Massive black holes will also grow. What is the dark energy and why is universe is expanding ever faster actually? They are the concepts. What is the structure and behavior of matter under extreme conditions? Right now, if hectic rainfall occurs, heavy rain occurs, you may not walk out of your home. How can you live? If it happens for about months together, you may not able to have your foods, grains, your things for living actually. It's a tough task. Agricultural activity will stop. Agricultural activity will vanish if we continuously pour, if the sky pours continuously water to a great extent. Will Einstein have the last word on gravity? Sure. Again, through the electromagnetic radiation, this is one of the map of the core. This is one with the how did the matter in the universe get to be so lumpy? How did elemental composition of the universe evolve? Okay. Is here you can see that what are the superstrings that can exist? How do we measure the size and the age of the universe? It is not an age. These are the lamps they can call. These are the arms. Earlier there were only 3 or 4 arms. 4th arm is identified here actually. This is the Milky Way shape of a Milky Way galaxy. Somewhere Earth is solar system and Sun is somewhere here actually. And this is the central part of the galaxy. Still we're having a photography of that kind. Now they're coming to not end actually, still. What happens here? If you allow the white light ray to pass through the spectrum, you'll get the Vip Gaia, no doubt. This Vip Gaia, having the spectrum, what it is shown either increasing in wavelength or decreasing in wavelength. Of course, as the dispersion goes, the Vip Gaia red should be on the top to a great extent, violet should come down actually. Okay. Blue, green, red are primary colors. What do you expect? Blue, green, red are primary colors. And no single primary color can create it from the other two. You can't create actually. Means to say that primary they are calling in such a way, you can't create red by combining those other two. You can't create the blue by combining the green and red, or you can't create the red any individual color. The blue. See, you can't extract the blue from green and red. You can't extract green from blue and red. You can't extract the red from blue and green. That's what it's called, the primary color, basic color of that kind. No primary color, no single primary color, in fact, can be created from the other two. But all other colors can be formed by combining these 3 primary colors. If you mix these three colors, you will get the rest of the other colors. Rest how many? 4. No doubt in it actually. Starting from violet, which is having the wavelength of 0.4 to 0.446 micron. Rest of the colors I have shown here actually. Sunlight is an uniform. Sunlight is made up of an uniform, or sunlight is the exists in the uniform or maybe in homogeneous color. It is actually a composite of various wavelengths of radiation in primarily under the ultraviolet, visible and infrared portions of the spectrum to a great extent, either ultraviolet or visible or maybe infrared. The visible portion of this spectrum, which is shown here, components of the colors, when sunlight is passed through a prism, which bends the light in differing amounts according to the wavelength. Depending on the wavelength, it has to bend. Depending on the wavelength, it has to bend. It's a dispersion. Those who have taught for +2, those who have taught for the graduation, those who are still taught and teaching for the master graduations are well aware. My presence and my discussion may not be an right part in this case. But thing is that these three colors differs from painter. Do you expect that this is for the electromagnetic energy which is emitting? Is it for an emission spectra or maybe an absorption spectra? My intention is that take these three colors, the left bottom corner, what you want to see that primary, secondary and tertiary. See, yellow has come. This is not with the emission spectra. This, if you want to paint actually, you ask a painter actually. Painter will never say these three colors. Painter use yellow as one of the primary colors. If you mix yellow, blue, you will get this color, green. If you mix yellow and red, you will get this color. If you mix blue and red, you will get this color. Okay. By this combination, if you goes, means primary is yellow, it can go to the tertiary as this color or maybe green color, or from this secondary color, it can go to the tertiary, again to the tertiary of this color. These combinations you can expect. How many are there? 7 colors. 7. How many are there? 7 colors. Is it 7 colors are sufficient? If you allow our ladies group to select a salary or maybe a dresses, they will spend time, unmanageable amount of the time till shop closes to select a proper color for them. Colors in a computer program or in nature are represented by combining the 3 pigments. Left side RGB is known as additive color of light. Again, in terms of the electromagnetic radiation, I am not deviating from my syllabus. The right side CMY, the cyan, magenta and yellow, subtractive colors of pigment. This is the additive. If you add them together, all of them, you will get the white. If you add them, all of them together, it is subtractive. It is subtractive in the sense it is a subtractive in the sense if you put them together, nothing is coming out of it. It becomes a black actually. You might have seen the umbrella painted with the different colors. If you rotate it, sometimes it becomes white and otherwise becomes black. These pigments are red, green and blue, which contrasts with primary colors by combining some amount of red, some amount of red, some amount of green and some amount of blue. Displayable color can be achieved. How many? There are 356 colors. 256 colors. 256 colors. If you put a 255 for the red, it is the maximum intensity where you can expect the first one. Minimum, if you go for the dark, lighter red to the lighter, it becomes dark red. 255 in the middle, okay. Green, light green or parrot green or slight green to the dark green. Of course, it was the same thing with the dark. Blue, again, the last one. If you mix them, all of them put together, it becomes black. Okay, means to say that if you see the left extreme here, all colors are merging. The dark blue and black color, you may not distinguish at all. If you put the 2 cloths or 2 materials, if they are of different colors, dark blue and the dark black color, you may not distinguish. It is very difficult. What are those things actually? They are not the colors. No color exists in the universe. That is the emission of a wavelength from an electromagnetic radiation. That is the emission of an radiation from an electromagnetic field in the visible range. Visible range starting from whatever the 400 to about 800, what you are expecting either in terms of the nanometer. There are 800 colors. Fine. My God. A beautiful thing. Hue is nothing but hue and saturation are independent characteristics of color. Take one blue, green, another one red. Mix them, put together. You will find the 256 colors. There is no doubt in it, actually. Of course, it is the combination of other color too, to a great extent. What you mean by hue? Hue refers to the wavelength of the light, which we commonly call color. There is no color. If you are saying blue, corresponds to some particular wavelength. If you're saying green, that corresponds to a particular wavelength. If you say cyan, that corresponds to a particular wavelength. If you say dark blue, one more wavelength. If you say light blue, one more wavelength of that kind. That is nothing but this. Being a physicist, being a science field, actually, if you want to say that, you have to clearly say that I want a shirt of about 6,500 angstrom wavelength. No other color can replica of that kind. I want a saree of about some 4,800 angstrom, or about 475 nanometer, or about 0.57 micron of that kind, not in terms of the thickness, but in terms of the color where it emits. You can have the unique color. 256 brands you can expect the same thing, not beyond that limit, except the change in the texture, change in the design and rest of the part. While saturation indicates how pure the color is, how much white is mixed within it. If it is high pure, you will have a dark blue. If it is here, right side. If it is mixed with white color, it becomes lighter. If it becomes pure green, there is no doubt. 256 for the blue, then can come back here. Maybe the red of that kind. For instance, pink can be considered a less saturated version of the red. Pink can be considered the lesser saturation version of the red. Here, pink and red, you can't expect. Blue and black, what I expect actually. Okay. No, sorry, I made a mistake here, there earlier. Black in the sense, you're saying white and black TV, white and black colors. Do you expect that? Colors means you will identify only with the waveguide, violet, blue, green, red, indigo. Is it black is a color? Is it white is a color? I need an answer from you before the end of the class. The infrared portion of the electromagnetic spectrum has two parts, the reflectivity and the emissivity. Two parts means one can reflect, other can emit. Means to say that if that is the case, can we take a photograph in these wavelengths? Yes. In the visible, there is no doubt. Can I take a photograph in the ultraviolet? Yes. Can I take a photograph in the infrared? Yes. Can I take a photograph in the X-ray? Yes. May not be direct photograph. What I want to say, there are some techniques to do that. There are photographic films in black and white, as well as color emissions, which are sensitive to the reflective portion of the infrared band, and these are used for scientific and artistic purpose to a great extent. But no photographic films exist to directly record the emissive spectrum. No photography is available for the emissivity. Observativity, fine. You keep the film, the radiation has to come and hit and interact with the material of the film. Then you develop that, it will come. Can you expect that? Or can you say that at least any photographic film exists directly which can record the emissivity of the infrared? No. If they did, then they would have to be cooled to a great extent and kept very cold during use, which would be practically impossible. However, there are a number of electronic devices which detect and record the thermal images and also infrared images to a great extent. Right? Yeah, here, maybe recently you might have seen that some of the images of moon are exchanging. About some pictures, they have 48 pictures of the moon by spending some 10 years by one of the scientists, they can call, who is scientist, who can observe continuously, no discrimination between the human beings at all. 10 years of moon. NASA explains moon shines in red, moon shines in blue, moon shines even in purple. Of course, did not be NASA. Even people from our department also can explain. There is no doubt in it. Those who are working on astro, atmospheric and planetary physics to a great, even common man can also have these things. Moon has, see the left diagram. Moon will never look like only the white patches, what you are getting a white ball, which are represented. If you see through the naked eye, may not. See, this is a clear picture with the huge revolutions, high resolutions. These dark spots are the mares they can call, shadowed regions they can call. These are the white regions are the mountain areas. This is continuously heated by meteorites, continuously heated by the electromagnetic radiation, continuously heated by the so many kind of the energy, because the moon doesn't have the atmosphere, feeble atmosphere. Moon doesn't, unfortunately, it is an unfortunate reason, moon doesn't have the magnetosphere also. If no magnetosphere, magnetic charged particles will come and hit to a great extent. They will not go and hit. In the en route, if the moon goes, sun emits the radiation all 360-degree solid angle. If the moon or any celestial body goes along the radiation which is emitted by the sun, certainly it has to undergo. We are under the ocean of the radiation emitted by the sun. Okay. And meteorites hit, continue. Volcanic eruptions will also happen actually. Moon is very active celestial body. Of course, it is an iron being celestial body. Moon has since forever been the most beautiful jewel of the night sky on Earth, unless you study it well. The planets, constant companion, undergo a cyclic change in its appearance, means that is the color, all thanks to the periodic reflection of light from the sun. This change in shape, of course, appears to be, its shape will not change, however, is not the only the different form of the moon, but takes in the night sky. The images have been collected by Marcel Pace, a primary school teacher and an astrophotographer by enthusiasts in Italy. It took, he took space of 10 years to capture all the shades of the moon. Okay, possible shades, whatever he mentioned. NASA explains that the next full moon, known by some as the Beaver moon, will occur at the end of this month until it goes back to its new moon stage by the mid of the December 2021. Is the rare blue moon, once in a while they can call, on the other hand, lights up the night sky when there are large dust particles in the atmosphere of either the moon or on the Earth, preferably on Earth. This means that light from the blue spectrum can reach the surface without getting dispersed on the way. Media might have created whenever the moon eclipses occurs, blue moon, reddish moon, gray moon, black moon, of that kind, no black. Okay, so many things will happen, disasters will happen. No disasters will happen unless until there are people, there are a scientific community, there are a good academicians to discuss it in a better way. This is one of the picture, no need to much discuss, just I brought it to that. See, this is mainly the interaction of the electromagnetic radiation with the atmospheric constituents like dust particles or charged particles, and also the molecules which exist on the Earth to a great extent, because we are here. If you take the same photograph from the space, it may not look like that. At times, it appears red somewhere. NASA explains that a red or a yellow or colored moon usually indicates the moon seen near the horizon. Horizon means just horizontal view, can explain. This is because the blue light gets scattered away over the long distance. It takes full moonlight to reach from the horizon to the Earth's surface, thanks to the atmospheric particles and the way which are including in the dust. Beautiful. Clouds don't actually exist. The colors don't actually exist. No blue color at all, no red color at all, no green color at all, no pink color at all. What you mean to say that? Whether I'm going wrong? What is my thought actually, the science? No, there are no colors. Apples and fire engines are not red. The sky and sea are not in blue, and no person is objectively black or white. The universe has light in different wavelengths, and color vision depend upon how our brain perceives the light of different wavelengths. If an object is having some blue color, all the colors are got absorbed or trapped, only the blue is emitted back, reflected back, scattered back from that object. That's why it appears to be blue for me. No blue color at all, no red apple, no even green, no red tomato, no other kind of a thing actually. No yellowish banana, no greenish banana of that kind. Technically, colors are the illusion created by our brain. Think of. See, stars glitter in the night sky. If you move away from the atmosphere, above the atmosphere to a great extent, it glows. No color at all. This color you are seeing in the atmosphere mainly because of the atmospheric constraints of the planets depends. Of course, this is for the Earth. majority of them with the nitrogen and oxygen, and rest of them with the dust particles of this particular size that will see later. Radio waves? No doubt. Starting from 30 kilohertz to about 3 gigahertz, the height of the Statue of Liberty, what you are expecting with the height, this amplitude and other things determines. Here, this is one of the microwave radio wave actually, and the with this huge dish of about 30, 35, 40 meters diameter. This is in the Parkes radio telescope we can call. They receive the radio waves from celestial bodies, even away from farther away, millions of kilometers, billions of kilometers. They can have the spectrum. On the left bottom corner, you see that this is the intensity calibration, or maybe intensity you can call, doesn't matter. This is with the different objects which are emitting. See that Earth emits somewhere here by its temperature of about 300 Kelvin on average. Jupiter with another temperature, with different in color. Sun emits somewhere here. All the spectrum actually here. Local phenomena here to a great extent. Here I want to say, radio telescope observatory is there in Ooty, RAC they can call, radio wave observatory. About 35-40 years back, it was not there. It was a recent establishment of the R&D. Professor Govind Swarup, he is no more, sorry, unfortunate for him. He passed away in 2017. He was the man behind TIFR and also from ISRO there to establish radio telescopes. Still, it was under the provision of the Britishers at that time. Later, it became a rule. Still, they can call it as a commissioner, they can call district commissioner. He went and asked the commissioner, he wanted to have some land for the setup of an observatory, radio astronomical observatory, RAC, radio astronomical observatory, RAC they can call, to see the planets. He was going every day. The district commissioner asked him in the sense, what is the lifetime of a star? Lifetime of a star is about 10 billion years. Right now, we are at the middle, 4.5 billion years is over, maybe for the sun and also for the universe we can call. 4.55 billion years is over. How long it can remain? Yes, sure, there is no doubt. Sun can burn with the same intensity, maybe more or less the same intensity and amount of the energy for another 5.5 billion years. Afterwards, it becomes white dwarfs and red giant and then nebulae. There is no difference. How long it will take the light to come? It's still billions of years. That commissioner has asked Govind Swarup, if it is a billions of years, why are you so hurry in establishing this setup at Ooty? The response by Govind Swarup at that time was, he himself has narrated this in several occasions. Lifetime of a star may be billions of years, but the lifetime of a human being is very less. We want to study, we want to know, we want to see, we want to enjoy our life by studying such type of the things. That's why he wants it at the earliest stage. It's only to a quote. My God, this is another, maybe the last slide, I hope actually. But still, I need another 10-15 minutes. When you see that here, what happens? IM wave. It is one of the beautiful picture of the electromagnetic spectrum. It covers the wide range, starting from the radio waves, FM radio waves, see that? Then maybe call cellular forms, okay? And then maybe microwave to a greater extent. Maybe the remote, what you are handling in your house to switch it on or switch it off. Any of the devices need not be a TV and allowed. Maybe the visible light between here, such a narrow band. Maybe the sunburn intensity because of the thermal. The medical X-rays will go here somewhere. And the gamma rays, including the nuclear reactors, how it works, which is the emission of the gammas. And in terms of the frequency, it can go from hertz, megahertz to 21 hertz of that kind. 1 megahertz to about 10 to the power of 15 megahertz or billions gigahertz, that kind actually. And you can see window here. This is the atmosphere is opaque to all the wavelength in this region. It does not allow. Radio waves can travel to a great extent here. Atmospheric is opaque again to this wavelength. Atmospheric is an optical window between infrared, some extent. Ultraviolet, no. Atmosphere is opaque to all the valences in this. Atmosphere allows 100 kilometer thickness of the atmosphere allows only the visible to reach here this place. What I want to say is that then when you tune your radio or maybe TV or send a text message or even pop up the popcorn in a microwave oven, you are using the electromagnetic energy. You depend on this energy every moment of every day. Without it, the world you know could not exist. That is the reason what I said a message to you for joining this class. Electromagnetic energy travels in waves and spans a broad spectrum from a very long radio waves to a short gamma rays, or in terms of the energy, low energetic radio waves to an high energetic gamma rays. A radio, the human eye can only detect only a small fraction of the spectrum. A radio detects a different portion of the spectrum, and an X-ray vision uses yet another portion. Scientific instruments use the full range of the electromagnetic spectrum, not by single instrument, remember, to study the Earth's features, the solar system, the universe, beyond the universe. Sun is a source of energy across the full electromagnetic spectrum, starting from gamma to the radio waves, and its electromagnetic radiation bombards our atmosphere constantly. All kind of radiation is coming and incident on the top of the atmosphere. However, Earth's atmosphere protects us from exposure to a range of higher energies. Thanks to the nature, it has created its own way. It is a good umbrella. It is a good shielding, actually, from exposure to the range of higher energy waves that can harm the life, harmful to the life. Gamma rays, X-rays, ultraviolet waves are ionizing in nature. I showed one picture. Compared to the gamma, alpha are ionizing a lot. They lose the energy so immediately, but the impact is quite high. Meaning, these waves have such a high energy that they can knock electrons out of the atoms. Exposure to these high energy waves can alter the atoms and molecules, and also can cause cancer, damage the cells by creating a cancer or to an organic matter. These changes to the cells can sometimes be useful, like in radiation therapy, or when radiation is used to kill the cancer cells, and other time it's not, as when we get sunburned to a great extent. Other way, this electromagnetic radiation is also reflected, absorbed mainly by several gaseous molecules in the Earth's atmosphere, among the most important being water vapor, carbon dioxide, and ozone. Not nitrogen, oxygen, and argon of that kind. Means this electromagnetic radiation is so important because that is why it is called the greenhouse gases. Some radiation, such as the visible light, largely passes through the atmosphere. Atmosphere acts like a window for such type of radiation. These regions of the spectrum with wavelengths that can pass through the atmosphere are referred to as the atmospheric windows. Some microwaves can even pass through the clouds, which make them the best wavelength for transmitting the satellite communication signals. While our atmosphere is essential to protect the life on Earth and keeping us and also the planet habitable, it is not very helpful when it comes to studying the sources of high energy radiation in space. It is another step. Sensitive instruments are positioned above the Earth's atmosphere and energy absorbed atmosphere to see light from energetic ultraviolet, X-rays, and gamma rays. Means the entire atmosphere is an hindrance to studying very low energy radio waves coming from space, as these waves are reflected by plasma in the Earth's atmosphere. Being this, I will have a small clipping, just watch it.
There's a lot of amazing and fantastic.
I need one confirmation that actually, are you able to hear voice?
Yes, sir.
Yes, sir.
Okay, fine. Sorry.
Yes, sir.
There's a lot of amazing and fantastic things occurring every day, everywhere, just yearning to be explored. It can seem in today's times it's harder and harder to find such beauty in the world, but that doesn't change the fact that it's there. The mundane yet fascinating functions of the everyday life are often overlooked, continuously plugging away in the background as everything moves about around them. For this reason, it seems appropriate that the first step on our journey of discovery is about the very thing that lets us observe such intricacies in the first place. I'm of course talking about light and why it's so interesting. And just about everyone, and just the thing that facilitates our ability to see. Light is almost always synonymous with the entire spectrum of electromagnetic radiation, spanning from radio waves all the way to the sinister gamma rays. Despite their differences in behavior, but still, what exactly is it? At some point in your life, you've heard the term light.
If possible, can you increase the volume, sir?
Are you not able to hear?
I am able to hear, but not that clearly.
Okay. Thing is that these are the media files. Actually, it will go like that only.
Okay, sir.
Otherwise, I will share the link later also. Sorry.
Okay, sir. Okay, sir.
One second.
Depend on it every hour of everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in radio transmissions in 1894 have spread into space for over 100 years at the speed of light. They passed Sirius in 1903, Vega in 1919, and Regulus in 1971. That signal has already passed over 1,000 stars. Anyone orbiting one of those stars with a really good receiver could detect Marconi's signal and know that we are here. Radio waves are the longest and contain the least energy of any electromagnetic to waves the length of cars, ships, mountains, all the way up to monstrous 2, a major discovery by Carl Janssen. Scientists can link the signals from an array of separate radio antennas to focus on tiny slices of distant space. Such arrays act as a single immense collector. This giant New Mexico array uses 27 parabolic dish antennas shaped into a giant across the globe, one of the largest, powerful telephoto lens that a baseball sitting on the moon would fill its entire field of view. Many of the greatest astronomical discoveries have been made using radio waves. Pulsars, the existence of plasma, which are among the largest objects in the universe, also provide more local information. Astronomical objects that have a magnetic field, wave sensors on the WIND spacecraft, record the radio waves emitted by a planet's ionosphere, such as the bursts from Jupiter, whose wavelength measures about 15 meters. Radio waves fill the space around us to bring entertainment, communicate magnetic radio waves, and then vibrate. First, let's find out. With wavelengths ranging from 30 centimeters down to 1 millimeter, microwaves fall between radio waves and infrared. Microwaves are used in Doppler radar, which is widely used for short-term localized weather forecasting and weather patterns and surface temperature, snow and rain, to reveal the Earth. The Japanese Earth Resources of recent deforestation, what they thought was noise from their instrument, for how our universe of light you can see. Back in 1800, William Herschel conducted an experiment.
Sorry, that you can continue, no issue. I will share that because it is getting time. If there are any particular queries, I can feel happy to answer to your query. Otherwise, I will stop sharing. If there are no queries, so try to exit one after the other. I will try to engage the class in next time. This is up to the electromagnetic radiation to some extent, actually. We'll in a discuss mode. If you're having any doubts, right now you can raise. Otherwise, you can raise later also. Thank you. Thank you, Nandal. Shall I end the meeting? End the class?
Okay, sir.
Okay, sir.
Okay. Okay. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.